I'm Shirley Fenton from the University of Waterloo. I'm manager of the Internet Project, one of the hosts for this seminar series. We're delighted that you managed to make it through the blizzard today. It's not exactly very nice, but it's made it through it today, so we do appreciate your attendance. This is the first of a series of seminars this year in our Smarter Health Seminar Series. This series recognizes the innovations, the contributions of private industry and joining with public organizations to deliver innovative solutions to the healthcare system. We're delighted today to have Kermani from Bycast to speak to us today. I'm sure that you'll be delighted with his seminar today. Just one little piece of logistics before we proceed. Our next seminar is February. It's February the 19th. It will be held here, same time, same place, and I'll be sending you out shortly an announcement of the content and the speakers for that seminar. If you are not on my email list or our snail mail list, please let me know. Write out your information for me, your email address, or give me your business card if you have a business card, and I'll make sure that you get on our information list for receiving announcements in the future. So without any more ado, I'll introduce our the co-host for this series, Dominic Covey. He is the chair in health informatics at the University of Waterloo and also the director of the Institute for Health Informatics Professionals. And he'll introduce our speaker.
Thank you, Shirley, and welcome to all of you. I'm glad you can make it here, or either that or it's such rotten weather outside that it's better to be here than somewhere else. Introduce Mo Kermani. I met Mo about a year ago. I was introduced to him by Bill Tatum, who is very well known at this university and been a major force in the university's advancement. Mo, turns out, I learned this when I was speaking with him as a physicist, did his PhD at the University of British Columbia. Don't worry about that, though. We decontaminated them before we got in here. And his PhD was in low-energy physics, which I thought was kind of interesting. It prepared you well, I think, for your marketing role, right?
Yes.
He worked at the Triumph facility, and then went into the area of speakers, I guess, sound systems and speakers, and worked with a company called Sonogistics. He was a founder of that company that makes still.
Yes, the company subsequently be acquired, but it still produces the product, yes.
Makes speakers, so I hope he'll be a good speaker. Anyway, having looked at his product, I got really quite fascinated by his work. I'm not a big person in knowledge about distributed systems. What I heard that Bycast had done was really quite impressive. When I heard then they had really made some inroads in British Columbia, which is a very difficult area for any company to really work with the health system. And it's got to be something good here. Some very, very knowledgeable people who are working in the health system, particularly the area he's in. I'll let him introduce that to you. The only request I had for Mo in doing this talk was not to snow us. We've already failed given the weather, but welcome, Mo, and hope you hear what you have to say. Thanks.
Thanks very much, Dominique and Shirley, for providing me the opportunity to come down and tell you about our work here at Bycast. So just a brief overview of my presentation. I'll start with some introductory remarks introducing the company, then talk in general about information technology in healthcare, talk a little bit about diagnostic image storage and transmission and some facts about digital imaging. Some of these may be known to some of the audience, but I'll discuss them. Discuss some of the traditional approaches for storage and transmission that are predominantly used in the industry today. Talk about GRIDS and the concept of grid computing as applied to storage. Discuss a clinical deployment of this technology and end with some concluding remarks. Bycast was founded in 1999. It is a privately held company, venture funded. It's located in Vancouver. The company develops distributed grids for the storage and transmission of bandwidth-intensive media. That includes images, video, and audio. with a particular focus on the application for the healthcare sector. The focus of our research and development has predominantly been on distributed system and content routing and content networking, essentially applying the same concepts that have been applied to the delivery of IP packets to the delivery of content. We've also done some work on network management and IP networking in order to make distributed systems easy to manage. And we spent a bunch of time doing work on distributed system security and encryption. Our vision is to create computing grids that can act as the storage and the transmission medium for the exchange of clinical records between stakeholders. That's our vision for our company. We realize that this is the holy grail, and that vision is big, and there are multiple barriers to entry and multiple barriers to making it happen. So, speaking of barriers, I wanted to take a few minutes to talk about new information technologies and healthcare, and sort of what the healthcare system views information technology, new information technologies as. There are two things that any solution must do in order to be successful. Otherwise, it should not be deployed in a healthcare system, because it is simply a tool. It must improve patient care, and it must reduce costs. I guess some people would argue what the order of these two should be. Some would argue that by reducing the cost that's associated with delivering care to each individual will allow more dollars to be spent, therefore delivering more care to more people and improving the overall quality of care. The concept of that this is cool, it's breakthrough, it's innovative, it doesn't matter, it doesn't count. Solutions that are introduced must be sustainable. We've seen projects that take shape, that get formed, that get deployed, they go through a clinical deployment, and then everybody goes home. And the equipment's left, and nobody's there to run it because the hospital doesn't have enough money to run it. So solutions must be sustainable in order for them to be deployed and to be successful. And it's all about solutions. It is not about technologies. It's about taking the technology and using technology to create solutions that solve real problems. In terms of the exchange of clinical records and clinical documents, the barriers to adoption of new solutions and new methodologies come from two areas. There are those that are technical, and there are those that are non-technical. On the technical side, a lack of standards and interoperability between various vendors' equipment and how these clinical records get exchanged is a big one. There's reliability. Often doctors today, when they write something on a piece of paper and they put it in a drawer and they close that drawer, they can walk to the drawer, they can pull it out, they can touch it, they can feel it. They feel that that information is available at their fingertips. When this information goes into a digital black hole, there has to be a comfort feeling that the system going down doesn't mean that I can't treat my patients. So the issues of reliability are key and often are overlooked, that so many enterprise systems are actually more reliable than are systems that are being used in hospitals today. And then there's issues of manageability. In essence, it cannot cost me more to operate a computer system or manage a solution than it costs me to manage the paper process. The technical arguments, the non-technical arguments are actually common, and they're common with any type of large enterprise software deployments. There are costs and lack of clear ROI, so the ROI has to be there. There's usability. The system has to be usable. And specifically in healthcare, because if you look at practitioners, clinicians, they don't have a lot of time for training. They don't want to be trained to use a new system. They have a limited window of time. They're completely overworked, and they want to use something with as little training as possible, with as few mouse clicks as possible, and be able to get their job done, because it is interacting with the technology. Although they may enjoy it in their spare time, some of them, it's not part of their jobs. They just want to do their job and go home. And sometimes you have lack of end-user buy-in. There's so many cases where hospitals have gone through and have implemented great solutions and nobody uses them because the doctors don't want to use them, either because they didn't have anything to do with how it was spec'd or because they just it's hard to use, but if it doesn't get used, it's useless. So essentially, the way we view things, it's about very focused solutions that solve very, very specific problems in the healthcare sector, and those are the ones that will succeed. So let's talk about diagnostic imaging facts. Some of you probably know this already, but imagery or diagnostic images are an essential element of the patient record. They are important. And the reports and the information that surrounds them is also important. They are big when they become digital. And the fact that they're big poses very unique challenges. It's also being accepted by users. The fact that standards have been around for a number of years, that PACS adoption has been very successful, means that digital imaging, to a large extent, is accepted by end users. There are those who still prefer to use film. But the benefits, the efficiencies that arise from migration to a digital environment have been clearly demonstrated and proven to the end user. There's no question. So there's the end user buy-in. An interesting thing that is happening, and that is the cost-effective deployment of IP networks, and the fact that IP network connectivity is spreading and is inexpensive, and the fact that there are multiple hospitals are coming into regions means that the regional access to this information is becoming a necessity. And this is a critical point. And in diagnostic imaging, you need access to historical data. In addition to the stuff you're looking at today, you need to look at the previous information. Again, I just want to make some few comments that are probably known to many people here. And that's images. What are diagnostic images? Are they just files? I ran across people that talk about a file. Oh, I can move a file around everywhere. Well, guess what? A file is not useful. When somebody goes in for a radiology exam, they get a study or an exam done. This is a complex data object that may be formed from thousands of files that are all interrelated together. These have to be delivered together. They have to be delivered in a certain sequence. That relationship between them has to be maintained. So essentially, when systems are designed to deal with these things, they must have to be able to recognize complex data objects rather than individual files. This is another very, very important point. So they're more than simple files. Let's look at some statistics in terms of what sort of happens, how much diagnostic work is done. Some of these stats they're amazing. I mean, in North America, there are 300 million radiology exams annually. And currently, or as of the date of this reference of 2002, they're predominantly still being created on film. That the world is not digital yet. The digital world hasn't caught on. But it's very, very interesting that the majority of the methods that are used to create complex images are inherently digital. MRI, I don't take a photograph of a proton spinning, therefore I create an MRI picture. The fundamental methods of imaging are digital for very complex imaging. PET, positron emission tomography, is digital. CTs, MRIs, to a certain extent ultrasound. You know, ultrasound, I have to have a computer that takes the sound waves and all the times and the phases and puts them together to create a to create an image. So you got all these things that are inherently digital, yet still we, to a large extent, use film. Interestingly enough, that as new technologies evolved on the imaging side, the volume of data that modalities produce is increased. So helical multi-slice CTs produce many more slices. New type of MRIs produce many more slices than the old generation of machines. So you have a new generation modalities that are fully digital that produce more data, more images. So what does that mean? In terms of the data size, I've got some samples here. And these are data from the field. I'm not talking about books. I'm not talking about vendor case studies. I'm not talking about things that are 5 years old. You go to a hospital, you collect stats on what happens on the ground today. So let's take MRI. An MRI image, typically each of them 250K. Studies can go from 100 to 1,000 images. Sort of the high end is sort of the new generation machines that hospitals are acquiring. So it's 25 to 250 megs. A CT, slightly bigger image size, slightly smaller number of images, depending how you look at it, 50 to 500 megs. A CR, which is your usual X-ray, everybody's fairly familiar with those. Not many of them, but they're typically large. They can be larger than 8 megs each. They can go as much as 15, 20. There are not that many of them, so 16 to 56 megs per study when you put all these objects together into this complex data object. And then you have these more sophisticated, more exotic types of imaging, such as cardiology, what's seen in cardiology. A Siemens cardiac biplane machine can produce up to 60 frames per second. I mean, that's an amazing amount of data coming out of this thing. And each of them is about 1.5 meg. So a study running for 30, 60 minutes or 2 minutes can consume a vast quantity of data. I mean, it's big. It's 600 to 5.4 gigs. It can be significant. So it's easy for a large hospital to consume terabytes of data a year. And guess what? They have to keep this data. They have to be able to retrieve it quickly. And it has to be available. And it has to be reliable. And you know what? If you lose the image or the study, that's not good. Because you no longer have the film that's off somewhere. And you've got to have the comfort level that the information that I put into this digital black hole that I can't see, I can't feel, I can't touch, exists and can be retrieved and it's reliable. And if anything happens to it, I can get it back online quickly. So this leads to the concept of data explosion. It's been talked about in sort of enterprises and in terms of digital media, but data explosion applies to the medical business as well. In essence, the economic benefits of going from film to digital are known. This is driving the data growth. That's one factor. The second factor is the new machines are producing more data than the other ones. So you got two factors that are contributing to the volume of data growth. So what does this imply? Well, there's the good news, and everybody keeps talking about the good news. The good news is Moore's with us. Moore's law applies. That, I can buy a computer 18 months from now that's twice as fast and costs half as much. And guess what? Disk drives are dropping in price. And I can buy the disk that was in my computer last year and it was 50 gigs. I can buy exactly the same thing for the same price now. That's 100 gigs. And this is supposed to solve my storage issues. So the good news is that the storage hardware is a commodity and it will continue to be a commodity. The bad news is that when you got all this data, it's not about where you put it, it's about how you manage it. So it's a management nightmare. So what does the management nightmare entail? How do I guarantee that I have fault tolerance and 24/7 reliability in a system that was 100 gig and now it's 1 terabyte and could be 10 terabytes? How could I fulfill the expectations of my users? That as my volume of data grows, the performance will remain the same that the users will have come to expect. How do I accommodate the fact that technologies become obsolete? And I need to have interoperability. I don't want to be locked into a single vendor. And really, how do I take advantage of the good news? How do I ride the curve down? How do I take advantage of Moore's law and the costs of the dropping costs of storage? It's a very, very critical element. So in terms of standards, just want to talk about standards. DICOM, Digital Imaging Communication Medicine, is the de facto, I like to call it, standard for diagnostic imaging. It's great. I think the world would not be the same if DICOM didn't exist, but clearly DICOM has some vagueness associated with it, and different vendors have taken the liberty of implementing DICOM in different ways. It is better than not having a standard, but it is not the same everywhere. So what does DICOM provide? DICOM provides the format, of course, but it provides an interface, a protocol for the communications, really, something that resides on top of TCP/IP, is a higher layer, but it allows for communication between devices. But the most important thing that DICOM provides is a comprehensive metadata framework. That the files include the data and the metadata, and that it is that metadata that is very, very critical to DICOM. At least in my opinion, it's as important as the format. So what does metadata mean? This is people often glance over the concept of metadata. So metadata is about the data. It's information about the data. The pixels are the information. Everything else that wraps around it that allows us to make use of that pixel data and actually turn it into something useful is the metadata. So the patient name, the modality, the description, the referring physician, all those things that we all know and love are the metadata. And metadata happens to be smaller in size than data. At the end, the data is useless without the metadata. So data, it is the combination of data plus the metadata together that form the information that are needed to do work. So let me now talk about some of the approaches. The traditional approach to diagnostic image storage and delivery is the centralized server model. Other people claim to not have this model, but the test will become clear. So various people acquire data and metadata, and they put that data and metadata into centralized data repositories, and people who want to get the data out of the centralized data repositories, they connect to it and they get the data out. And this works well for some applications. It's a mature architectural approach. It is well suited for small data set, and it works well for small geographic footprints. It's really important to emphasize the geographic footprint. And the security model is actually quite simple in this kind of an approach. You take this from a physical security standpoint, you take your server, you lock it in a room, you close it, and you put a gateway in, and access to it is controlled. So it's a relatively simple model for security. But we think it's yesterday's technology. Well, it actually happens to be today's technology, what everybody uses at the end, but it's really yesterday's architecture. So what are the downsides? It's really cost. If you look at expensive multiprocessor servers, high-performance storage subsystems are required to really operate such a thing. At the end of the day, you have single points of failure in this kind of an architecture. There's scalability. You can't really simply scale this system as you go along with no impact on the users. And they don't scale well to geographically dispersed users, all of whom may be connected with networks of limited bandwidth connectivity that are unreliable. There's accessibility. They're very well suited for expansion beyond. They're not suited for the expansion to areas where there's limited bandwidth connectivity. So the solution, everybody says, move to a distributed model. Well, I find it very frustrating to the fact that the word distributed computing has been ill-defined and misused continuously. Well, what does distributed mean? Well, distributed computing is not about creating islands of information right off the bat. It's not about creating this storage system here and this one here and this one here and this one here, putting various pieces of data on all of them, and then saying, oh, where do I have to find my data? That's not centralized. And I can say that splitting a centralized server into multiple components is not a distributed system. So I have A to F on this server, and the rest on this server, and some of it on this server. That's not distributed computing. And let me tell you that managing multiple network attached storage attached to a central database is also not distributed computing. It's an approach. It's an attempt. So
This is what I like to call another centralized approach, which is one big database managing a bunch of storage devices. One control system. And that control system, if in the sort of the first generation control system, data still goes through that main subsystem, and it gets stored on the storage elements that are attached to it via networks. The sort of second generation is a centralized control system with multiple network attached storage elements. The data goes into each of them. But remember, the metadata is stored in the database. There's the metadata and there's the data. Don't lose the fact of the metadata and the data. You need the metadata to do searches. So this is still an extension of the centralized approach in computing. It's simple to do. So central databases control all knowledge, and single points of failure remain. Scalability. Query scalability is accomplished by throwing more processors into bigger boxes. Or let's split our database into two databases from A to M or from N to Z. And they don't work very well, these types of approaches, when they go over WANs. Because typically they use network file systems. Oh, we have to be part of the same NT file domain, and we got to mount all these partitions all over the network. They rely on the inherent underlying operating system to a large extent to achieve network connectivity, such as NFS and all those other things that are really not meant for this kind of thing. And so the expansion of the geographic footprint becomes a challenge. The grid architecture, what does it mean? Really, the grid was inspired by the success of some of the most complex and the most reliable systems that exist in the world today, including the power grid and the telecommunications grid. A grid, when you go in your home today and you plug your light into that socket, you draw power out of the socket. That power is generated by multiple power generating stations all over. Turning one of those power generating stations off does not result in a blackout. Turning additional power generation station on does not cause the voltage to go to 220. And the grid grows. If there's another city, you simply expand the grid. If you need more power, you turn on more power generating stations. And if you need less power, you turn them off and decommission them. You upgrade those power generating stations on the fly without turning the lights to everybody off. So in essence, the grid is the concept that you're able to abstract the management of resources, faults, and the recovery from faults. That's done automatically, without the knowledge of the user and without centralized control anything. There's no single anything. It is a collection of elements that together looks like one, and it provides computational utility. It allows computational problems. In grid computing, where grid computing is used for processing power, problems get run on the grid. And as another node in the grid comes up, there's the grid. It's got more power and it can run more problems, solve more problems. And it's composed of many individual components that are not the same power, they don't have the same capacity, they don't have the same resources, they're not made by the same vendor. So I was reading Ian Foster's book and an article that he wrote. Ian Foster is an expert on grid computing, Argonne National Lab, University of Chicago, and he has the grid checklist. So what makes a grid? That the coordination of resources is not subject to central control. Not one single point coordinates resources. That there is use of standard protocols and interfaces, and that the system provides a non-trivial quality of service regarding speed availability or other things that might be important to the usage. What we're talking about is applying the concept of grid or grid computing to storage, and this is something that's taking place in the world today. It is taking place predominantly in high-energy physics experiments, locations such as CERN in Europe, that they're trying to build these grids for moving terabytes of data around the world. You're talking about multiple heterogeneous, distributed and individually unreliable storage and computing elements together. But what they look like is they look like a unified storage system. They look like one. And they have no single points of failure. The concepts of content storage, directories, metadata storage, and query and security, and the management of the resources as being storage and processing power are abstracted. And the recovery from faults and reliability is also abstracted. So basically, grid storage is not about hardware, it's software. It's software that operates on many individual computing components, nodes, that each manage some storage element. That storage element can be a disk, can be a RAID, can be a fiber channel SAN, it can be a network attached storage, it can be anything. It can be any storage technology you want, as long as you can store data on it. And they are interconnected over an IP network in a mesh topology. In essence, that between every point and every other point, there are multiple routes. And this mesh could be both logical as well as physical. Typically logical in most configurations. And these links that connect all these nodes together, they have different bandwidths. And they may be up and down, and they're completely unreliable. So you've got to connect these things together to form a storage grid that can store and transmit diagnostic images. That is what we have done. That is Bycast Endeavor Imaging product. So picture's worth 1,000 words. So let's talk about, so here, instead of deploying centralized servers, you deploy a grid consisting of many individual nodes. This infrastructure, we refer to it as the content network or the grid network. It works with all the existing things that exist in a hospital environment today. It works with PACS, it works with viewing workstations, as long as the interfaces between the systems that are on the outside and the grid conform to open standards. So the interfaces into this system are based on open standards. The way data comes out of it is based on open standards. You can put data into any node within the grid and get that data out of any other node within the grid. Every single node in the grid can respond to queries. And there is no central point for the storage of metadata. There is no single master database. The metadata propagates through the system. More importantly, is the grid is aware of the network and aware of the content. In essence, you can determine what is the best path, for example, to get an exam from a single point to another. You can say how many replicas of an object can reside in the grid and where they have to reside in the grid based on programmable business logic. So you basically can set up real-time data backups in 1, 2, or n locations. This is actually one of the things we're doing as I get to the clinical deployment, is the ability to basically eliminate the near-term backup strategy that a lot of people have to use to protect large volumes of information. So it's a cohesive system that looks like one. You can, once you put a piece of data anywhere in the grid, you can get it out of anywhere, and the metadata propagation happens. It's aware of it speaks DICOM. It's aware of DICOM. It's not some proprietary mechanism, and it knows about metadata. And you can put anything through this grid that you want. You can put an image. You can put a video file. You put an audio file, or you can put an Adobe Acrobat document, if you wish. The interfaces to the external devices are based on standards. Or you can hook up a web server and save images over the web, if you wish. The idea is that this is complementary to the existing infrastructure of PACS that exists in the hospital. It allows you to expand the capacity on your PACS in terms of the storage and the back-end archive. It allows you to expand the footprint capacity of the PACS, hook together multiple PACSes to form regional PACS. It is not meant to displace the PACS because it fundamentally does something different than the PACS. It's used, for example, at the cancer agency to work together with their PACS but provide access to diagnostic images through the electronic health record. So you can tie this into the electronic health record to provide images for enterprise-wide through the electronic health record. So the architectural highlights. There's no centralized anything. There's no centralized control system or master database or active database versus hot standby database. Everything is active. It is fundamental distributed computing. It comes with some challenges. And let me say, for those, we're not trying to propagate information faster than the speed of light. So the laws of causality in physics still apply. It's important to note that both the data and the metadata are distributed. It is about heterogeneous hardware and components, each of which manages a different storage element. It is completely aware of DICOM, so it understands studies, series, associations, all those good things, DICOM queries, etc. And communications with external systems is based on open standards. If you're talking about images, it's DICOM. If you're talking about some other metadata exchange, it could be HL7. You're talking about serving web pages or serving content over it could be HTTP, HTTPS for secure transmissions, RTSP for the transmission of real-time media, live, or data that is streamed down. It is aware of the network. The grid is aware of the network as well as the content. It knows the bandwidth between various parts and how to get the content from one place to another. And this is the concept that I talked about, is intelligent content-based routing. It's about routing content, routing files through best paths. Sort of at a high level, I won't speak too much more detail. You have a reliable and secure storage and transport mechanism down here. There's a content routing algorithms that stand on top of it. These content routing algorithms take application-specific business logic, such as data that might come from scheduling systems, etc., to send data to various places. But as well, they take information, resource information, such as load, link weighting, the instantaneous bandwidth available between various links, to make decisions. One of the critical elements is metadata validation. They can interface with external systems to validate metadata, and the changes to the metadata that may come from an external system, such as a hospital health information system or a radiology information system, can be propagated through this, both at the file level as well as at the metadata level, because there are some specific rules, such as pediatric work, where the actual file may have to be changed. For example, if a child gets adopted, they had an X-ray, you want to eliminate all the information that's buried and part of the individual DICOM file, so when you dial up the DICOM file, the name of the child doesn't show up. So you can change both the content as well as the metadata. And what comes out is relevant information for usage, statistics, and audit and reporting that can be generated in real time and propagates through. So what is the advantage? It costs less and it's higher performance. It costs less and it's higher performance because it combines multiple individual computers and storage elements into something that's much more performance, will be always much higher performance, and will always cost less than any single centralized approach. It provides better quality of service because there is no single points of failure of anything. It provides greater scalability. You do not have to take anything down to add nodes to the grid. As you expand the grid, you simply add more nodes. Whether it's within one facility that you want to expand your storage, across facilities, you want to expand the footprint, you want to put a node in one department to get faster access, you expand the capacity of this network without impacting the users. And that is really critical in a 24/7 operation. You cannot rely on the fact that I will take your system down for 2 days. Or my new software upgrade didn't work and it's going to take me 2 days to roll it back. In this kind of an architecture, you can actually do live software upgrades on a subset of nodes, and if things don't work out, you just turn them off. So what happens if your grid storage system and node explodes? What do you have to do? You have to do nothing. You actually do nothing. And it gives you enough time to be able to understand the situation and react to the situation in case there are faults. And this is very important for IT staff that are under pressure to get the thing working. And you can, last but not least, you can expand the geographic footprint on an as-needed basis. So what are the technical challenges? One of them is, believe it or not, is security. If you have more points, you're more vulnerable to attacks. If people can get into this grid from one point, can they do nasty things? So security cannot be something you bolt on, that you buy from somebody and you bolt it on the side and say, I'm now secure. It's got to be an integral part of the architecture and an integral part of the design. There's management. Centralized management is key. You cannot have distributed systems that are hard to manage. And distributed systems are not harder to manage if designed correctly and corrected, and they have the right management software. There actually is the management software that makes systems, the inadequacy of management software that makes systems difficult to manage. And there's the issue of metadata consistency and synchronization of metadata across a large network. And I'm not talking about using Oracle's replication algorithm to replicate between two databases, because that's over-designed, doesn't work over a network of limited bandwidth connectivity, and it's not really meant for this. I'm talking about fundamentally new approaches to database algorithm and data synchronization that must take into account the fact that conflicts can arise and decisions that are made must be consistent between various nodes. I'll talk about this a little later. So what did we do in terms of security? Everything we transmit, everything we store is encrypted using well-established encryption algorithms, including advanced encryption standard. Everything, including the network and the communications. There's a mini PKI infrastructure that's built into the system for authentication various nodes. So as nodes want to communicate with each other, they have to authenticate. And there's a mechanisms we've put in place to ensure that not anybody can come up and impersonate a node and be able to get data. There's integrity verification on the fly. We use checksum algorithms and to verify that the stored data that you have, if you have 5 terabytes of stored data, it is valid data, because a lot of times your file system will not do database integrity validation. The only time you know that the file was corrupt is when you went to get it, and that's too late. So we do continuous database integrity checks in real time when the system's not doing anything else to ensure that there's integrity maintained. There's detailed audit logs. In essence, audit logs are created from all system activity, both for proactive analysis and security reasons, but also in order to ensure that administrators and decision makers can plan accordingly. We've designed this to meet the guidelines that are set out by HIPAA, and includes emergency access and other mechanisms that are required to meet this criteria. The management is a web-based system that is comprehensive. It is based on telecom standards, and it is not some freeware that we got off the net. It is built to achieve the goals that we set out, which is how do you manage a distributed system that can be spread over a wide geographic region from one location. It provides comprehensive management of DICOM, attributes and statistics, of storage, of network, of bandwidth. It provides historical and real-time reporting statistics on all system parameters. Automated fault detection and alerts can be delivered via wireless devices, email, or fax. There's automated device discovery, so that if you plug in a node comes up, it automatically registers and it joins part of the network, so you don't have to go and add things by hand. And it's really a telecom-grade network management system. Sort of to give you an idea, so if you look at a network that would be spread across the US, this is a hypothetical example, some screenshots. You can drill down, you can look at the region at a regional level. You can drill down to individual components and look at the DICOM subsystem, the storage element, the network element for each of them. You can generate historical reports on all system activity in real time, including things that are relevant to the user. How many DICOM associations do I have? How come my C-store took 5 seconds longer today than it did yesterday? And you can customize a variety of alerts that are automatically triggered as system parameters change. Either your storage becomes too big, too small, too much, not enough space left, the network link goes down. So you can customize all these storage and they can get delivered via email or pager. So it's a proactive steps in making sure that you can avoid faults. I want to come back to the problem of data synchronization in an environment where you have to accommodate heterogeneous databases. So there is no way you want to do anything directly to the database ever. You want it to work over a wide area network. You want it to handle what's called islanding, which means one node becomes disconnected from the rest of the network. And when it joins the network, it has to be able to reconcile its data and synchronize so that you have consistency across the network. You have to be able to address conflict resolution. And conflict resolution is as much a business issue as it is a technical issue of how do conflicts really get resolved. And most importantly, you must arrive at the same decision everywhere within the network, given that information propagates at a finite speed. So that's the key. Information propagates at a finite speed. In terms of the clinical deployment, we started down this path with the BC Cancer Agency, which is a branch of the Provincial Health Services Authority in British Columbia. BCCA is responsible for all of cancer treatment across the province of BC. It has terabytes of images that it produces internally, as well as it acquires data from other organizations. It operates an enterprise-wide electronic health record system that includes everything that has to do with patients. That includes their lab results, that includes their images, reports, documents. And there are lots of specialists that need to have access to the entire electronic patient record. Actually, typically for cancer treatment specifically, where it's a complex treatment process involving many different individuals, you have multiple people that may be in multiple locations requiring access to the entire spectrum of the electronic health record, including diagnostic images. So what they had was everything else, including the diagnostic image part. What we added to them is the diagnostic imaging component. We deployed a 6-node network across 3 locations. It's got 1.8 terabytes of triple replicated data. They wanted the data to actually be stored in 3 separate places in off-site in real time. So you could have loss of connectivity as well as loss of equipment. That's a total of 5.4 terabytes of managed storage. That's managed by the system in real time. We're actually doubling the capacity of this system to over 10 terabytes as we speak. And this is being done on the live system. The actual physicians don't even know, because we turn node off, we double their capacity, and they come back on, and they just join part of the network and they act. Very important. Scalability on the fly, as you need it, when you need it. Cost less, does more. So this is sort of a diagram of it. The system actually connects 3 various hospitals. There's the Vancouver Clinic, Vancouver Center. At each of these centers, you have modalities that generate data internally. You have data that comes off from remote clinics that may be stored on CDs. People look at this information on high-quality diagnostic workstations, as well as lower-quality clinical workstations that are spread throughout the hospital. In the Victoria Center, the same thing. And this we linked together actually with the Children's and Women's Health Center of BC. And the reason is these are all part of the Provincial Health Services Authority. And the acquisition of pediatric oncology images is occurring actually through Children's and Women's Hospital. They already had what they call their health information system. RIS, HIS is actually a comprehensive enterprise-wide system for managing the entire operation. And we deploy, and there's a network management interface that allows them to monitor and manage. And there are 2 nodes located at each facility. Data can go anywhere, can come out anywhere. They get proactively pushed, cached, and retrieved as on an as-needed basis. And they interface with the standard DICOM viewer software. That's the clinical deployment. I want to, before I finish this presentation, I want to thank the team at Bycast that's formed by some of the brightest minds I've ever had the opportunity to work with. They come from a diverse background that includes telecommunications, IP networking, encryption, and security. They're David Slick, Oliver Seiler, Keith Ma, Tim Altman, Mike Montour, Walter Persilo, David Terry, Dale Muir, and Juan Eng. I had to say everybody's name. Part of the deployment that we've done for the BC Cancer Agency has actually been funded by the Canary Telehealth Program. And I'd like to thank the staff of the BC Cancer Agency for working with us, especially Chris Lucky and Midori Kawahara. And in conclusion, we're presenting a new approach to the storage and transmission of large data set. And we're doing it by taking an approach and creating a solution that's tailored to the unique and specific needs of the medical community, specifically diagnostic imaging. We've proven this in a live clinical environment, and we're presenting 3 papers on Medical Imaging 2003 at SPIE. So if you're there and you happen to see our papers, have a read. And they are on the security framework, they're on the management framework, and the grid, distributed grid as a whole. Thank you.
Well, thank you. I think you've also done one of the best presentations we've heard, so it's very, very enjoyable. Questions and comments from anybody? What I'll ask Mo to do too is repeat your questions so we get on to it. We only have one microphone today.
How can you go live on some nodes without affecting all? You have to take them out of...
No, the nodes can go into what's called either read-only mode, or they can completely fall off. And because of the rules that are applied to the database data replication as well as the metadata, the requests that come in go to alternate nodes. So once you take a node offline, the information that was available on that node is obviously not accessible because it's physically not connected. But because you have redundancy built in through multiple nodes that stores typically the same information, and that's a configurable business logic thing, you're able to take that node offline. This was actually a very specific implementation where we had a really specific request to take nodes offline. We prefer, and the approach to increasing capacity is really adding more nodes, because as that node comes on, it literally provides additional storage resources that can be managed and automatically. So once you take a node offline and you bring it back online, it's basically islanded and disconnected from the network for that period of time. It needs to handle metadata reconciliation. It needs to be aware of what else the sister nodes or neighbor nodes process so that it can come up to speed and be linked and synced with the other ones.
And when I've heard you talk before, I reflected it's almost like a RAID disk array,
yes,
except physically distributed.
Absolutely. Yes, it's sort of the concept. I mean, it's the concept of RAIN. I mean, RAIN was introduced by a NASA scientist back in 1988 for the delivery of video. But it was actually not used over wide area networks and wasn't aware of metadata as much. So this is similar to RAIN, if you will.
I understand that concept. My question more relates to the comment that you made where you could take your nodes and use them for live upgrades for a new version of the system, and then if that doesn't work, you can turn them back off again.
Right.
Now, how can you do your testing without affecting the rest of your system?
The issue is that...
That offline.
No, that has to do with how you architect the interactions that occur between nodes. If your interaction between nodes are very, very well defined, your as far as this other node is concerned, and when it talks to this node, there's a series of interactions that take place. These interactions are the same, regardless of what this node is. So if this doesn't work, something goes wrong with these interactions, and you've got to make sure that if anything goes wrong, it doesn't affect the integrity of the whole system. So if something doesn't work, you can turn this off, and the system will function. So it is precisely because of those things that the architecture and the interfaces have to be well designed with a distributed computing hat on from the beginning, from day one, rather than sort of trying to go distributed halfway across.
Don?
A few more details about the components in the grid and their architecture?
The components of the grid really consist of three parts. One is called a media router, which is essentially a high-performance router, content router, if you will. There's a distributed business rules engine that sits on top of it.
Is the routers themselves distributed?
Yes, the routers themselves are distributed. There's no single point of anything there. And you can bring nodes up that have routers and business rules, or routers alone, or business rules alone. You can sort of break it down at different levels, at different hierarchies, if you want, even within each group or each cluster.
Actually, it is basically what you mentioned about this RAID. It's something when you have so many nodes, you can only disconnect so many.
Yes, you can only disconnect.
So you have for the synchronization, right?
It's not synchronization. It has to do with the fact that in a typical RAID 5, your first disk failure is okay. You yank the second, one out, or you yank the wrong one out. You got a problem. And this kind is the concept of, instead of RAID, you have the concept of replicas, where if you have more nodes than replicas, and you turn all your replicas off, then there's a problem. Yeah.
Yeah, you mentioned that the need for any sort of a backup is minimized, but I don't think it's fully negated because of things like accidental deletion and stuff like that.
Absolutely, and I think you have to build mechanisms in there. First of all, we never delete anything. So you have complete version control of the way systems are architected. So you never delete it. You mark it for deletion and you can delete it later, or the system, has business rules with regard to how content deletion takes place. I don't see a reason why you would do a backup other than simply if your volume of data grew so large that instead of doing backup, you really needed to do hierarchical storage management. To address that issue, each of our nodes can also interface to a tape drive, so that just becomes another storage element that it manages. So your hierarchical storage management really becomes a side effect of this distributed grid architecture. And you implement business rules that the data will automatically migrate to a node and be stored. And not only that, but your metadata is still aware that that data is now archived. And you can use that information to retrieve it.
Okay. Do you have a sort of natural minimum size?
Their natural minimum size is 3.
And the cost?
The cost is on a per node basis. It depends on the way we typically work in an environment is that we recommend a content network design based on the number of modalities that are at the hospital and the volume of data that create and what they want to do in terms of the geographic separation for disaster recovery planning. Based on that, we recommend the number of nodes, and then we price accordingly the cost per node. I can share the details on what the individual costing of the nodes are with you following the presentation if you wish.
Any questions here?
Your clinical configuration has 3 nodes, and I assume that anyone wanting to search for data within your grid would ultimately the query or some kind of search would go to all nodes in the grid. And I'm wondering if you have sort of a compromise, I guess, between size of the grid and performance, because ultimately as the grid gets larger, your performance is going to be negatively impacted.
That's true or not, and not, because the metadata layer is actually spread horizontally in terms of topology as well as vertically. So as your grid becomes large enough, you actually have several lower, so if you think of the metadata as the part that's the searchable component, you can have several lower metadata nodes hooking up to a higher metadata node that itself is distributed across. So say you've got 100 nodes that's spread into groups of 5, groups of 10. Then you have 10 higher metadata nodes, which the query will just propagate and go to these instead of going to one centralized location or having to go to all the nodes. It's the actual path by which you propagate the query through the network that determines your performance.
Just to follow up, I guess, but you also mentioned that some of these nodes could be connected over low bandwidth, and I assume you're talking like over dial-up type of connections, or.
When I'm talking about low bandwidth, I'm talking about DSL. I'm talking about like 700 kilobits to say 1.2 megabits per second.
Related to that, you also have a routing capability, so if you do have low-speed nodes, you can go around those.
That's correct. Because the system is, so you have link weighting. If you have multiple links between, when I mentioned the concept of link weighting, the link weighting takes into account the cost as well as the bandwidth. So if you have physical network connectivity via different paths to a certain node, you can actually route content through that path. In a lot of cases, the physical network may be the problem, so that doesn't really get around it. But you can do, if for centers with limited bandwidth connectivity, you may be able to take advantage of information that comes from external system to really, so it's sort of the concept of prefetching, but across a much larger geographic region to be able to migrate the data to the areas where they're needed.
Referring back to that third question, so you say you have some lower level nodes that handle the metadata?
Imagine what I said is there are 2 tiers, right? There's the metadata tier and there's the data tier. The metadata tier, you can, as your grid grows, you have these nodes that have local knowledge of the metadata in a certain region. And you have, as you grow up this scale, you have nodes that know about more metadata. And you don't necessarily have to go everywhere to find the query. You just have to get enough hierarchy as your grid grows. You just need to move higher on this plane in order to get to a level where those nodes know about your data. So if you think of a topology, it's more spread horizontally as well as vertically.
So are these nodes hard-coded?
No, no. Well, the nodes, if you get to a grid of that size, you have a selection to choose from. There's actually a provisioning process when you install the software. Because of the security, that you have to generate certificates and all those other things. You provision your node and you define what the content network topology looks like. And you do that through a computed automated process that we sit and we design content networks. The same way an IP person would design their network.
So all the data communication takes place exclusively on the server. There's all exclusively on higher-end machines that are talking to the workstations, for example.
The workstations are completely different. The workstations are like clients. I think of the workstation, they don't know anything. They just ask. They connect to their nearest node and they talk DICOM. They don't know anything. It's completely server-based.
If the high-energy physics people do grid computing, are you more of a packager of that open system technology?
No.
Or do you add?
So the grid computing is a general area of research that has been, it's the same as, client-server computing. It's sort of an umbrella that encompasses the computing, the attempt to abandon the notion that I have to get faster server and try to solve problems on a collection of machines. This is being applied in different areas. What we're doing is we're taking, the technologies we've developed is completely been developed from scratch by ourselves. We're not borrowing anything from any other group. But what we've done is developed something that's very, very specifically and tailored to medical and specifically diagnostic imaging. But the point I'm trying to get across is these concepts are getting traction in other areas in the computing world where large data sets need to be managed and large problems need to be solved. So it's a trend that is happening in computing. It is not an isolated thing.
Any other questions or comments? What is the term Bycast?
I mentioned to Dominic this before. The name Bycast is completely by accident. It had to do with the fact that when we originally started down this path, we were actually using the grid to transmit real-time video. And the notion of broadcasting was in place. And this was the only domain name that was available, Bycast. And the founder of our company searched bycast.org.net, and that's what they found. So that's where the name came from.
Sort of a name of last resort?
It meant it in the context of the internet broadcasting and the IP world, but it doesn't have any specific significance.
Any other comments or questions? Well, thank you. Charlotte?
I want to thank Mo for a very interesting talk. I was quite fascinated by the whole approach that you've taken, and I think its applicability to the healthcare system will be fascinating to see how it grows into that domain. So I thank you for coming out today in such inclement weather. We hope that next time that we meet together, it's much better, maybe Vancouver weather at that point.
If you want rain.
The date that we'll meet again is February 19th, and I look forward to you coming in. If you have further questions that you want to meet with the speaker, we'll have